Hello, good afternoon. Thank you very much for your time. My name is Chris Mee. I'm from San Diego State University, and today I will deliver a talk on Second Life EV battery. So let me share my screen so that I can start the presentation. I need to switch this one to this main screen. Thank you. I hopefully that you can hear me very well. So as I said, I'm a distinguished professor and chair of Department of Electrical and Computer Engineering at San Diego State University. So today's talk is about cost-effective integration of Second Life EV batteries with a solar PV system. The background is that we know that grid-connected battery energy storage system, it can manage the variability of power generation from renewable energy, such as EV, wind, and solar systems. This energy storage system can also reduce peak power demand and shift usage to shift off peak hours and reduce electricity cost. However, these systems are typically very expensive. Their return on investment is not very well. So on the other hand, Second Life EV batteries are coming widely available in the next couple of years, and it will be more and more in the future. This can be discarded batteries, in-warranty replacement, test vehicles, unsold batteries, accidents, and so on. These batteries, they're not good anymore for road driving, but they still have capacity left. So we know that these batteries are expensive to manufacture and recycle. Making use of these batteries in their second life can help improve the environment, reduce EV owner cost, and benefit businesses. However, there are barriers to use Second Life EV batteries. First of all, we need to develop and integrate these batteries reliably, cost-effectively, and economically. We also have to safely and consistently manufacture these systems and deploy them. The hurdles we have to overcome will include proper removal of batteries from EVs, transport them, storage them, testing them, and select the good batteries for second life use and send the bad ones for recycling. We need to develop a quick, simple, and accurate battery health estimation method for every cell within the storage system after deployment in the grid storage. We need to develop a dynamic battery management system that can minimize the degradation, optimize the usage so that we can reduce the cost to the maximum for the building owners. So the scope of this presentation include the aging study of a second life EV batteries in the laboratory. Through that, we also create a second life battery genome through laboratory scale analysis. We develop a battery management system, associated technologies, algorithms, and operation strategies, which can increase overall efficiency, reduce total ownership cost, and decrease the degradation of these batteries. We design and build 2 pilot testing facilities to demonstrate the proposed technology. The goal is to demonstrate that these batteries can last enough time in their second life that can also help the owner to save overall investment or to maximize the return on investment. The first step we do in this study is to characterize the second life EV batteries. We selected 4 types of EV batteries for the study. The first one is a Nissan Leaf Gen 1 battery. It's we tested about 100 packs. They all have a SOH anywhere from 60 to 70%. The second is the Nissan Leaf Gen 3 batteries. They have a much higher capacity, anywhere from 89 to 97%. The reason for the high capacity of Nissan Leaf Gen 3 is that these batteries are only in the field for a few years. They are from warranty or marked batteries. The third category is a lithium iron phosphate battery from forklift, and the last is also lithium iron phosphate battery from electrical buses. As you can see, the forklift has a cell capacity at 89, but the pack level is only 50 to 60. The electric bus is similar. They have 80% SOH at the cell level, but 52% at the pack level. So therefore, the last two categories of batteries needs balancing before they can be deployed in grid storage applications. After testing of these four types of EV batteries, we have found that the initial SOH of these batteries are pretty good. They also have a balance issue in the last two categories of batteries. Their capacity is roughly 20% per 1,000 cycle degradation, and 4% in 1,000 cycle in the slow and the battery storage applications. If we manage these batteries well, they can be used for 10 to 15 years or up to 20 years, depending on the type battery and usage condition. However, for the lithium iron phosphate battery, we need to address the balance issue before they can be deployed. We started with battery pack testing, including the Gen 1 and the Gen 3 battery, the Gen 1 on the left and the Gen 3 on the right. We tested the battery packs, and also we tested the cells from the battery pack for Gen 1 and also Gen 2, Gen 3. The Gen 1, we tested 2 battery cells, and Gen 3, we tested 24 cells, both including the room temperature for the pack level, module level, and the cell level. We disassembled the battery pack to get the module, and then we disassembled the module. Of course, this is another module to get the cell for our laboratory testing. The testing included room temperature, as well as inside the thermal chamber at a low temperature, like 10 degrees C, and high temperature, like 35 degrees C. The results are shown here. The Gen 1 battery shows a very consistent and linear degradation in their second life. They can last up to 5,000 cycles after their first life use. However, you can see their battery impedance increase linearly, non-linearly, in fact, after 3,000 cycles in their second life. So a good point to retire these batteries from their second life is around 3,000 cycles. However, in applications where the power demand is not very high, this battery can continue to be used for another 3,000 cycles if, again, the power demand is low. For the Gen 3 battery, it is interesting to note that these batteries don't last as long as the Gen 1 battery. They typically last about 1,000 to 1,500 cycles before they experience aging knee. As you can see from the top graph for the capacity, the aging knee happens very quickly. After the aging knee, the degradation goes very dramatically. Therefore, this battery needs to be taken out of service. For the bottom graph, you can also see that the impedance increases dramatically once the aging knee happens. So it is important to identify this aging knee so that we can make sure these batteries are taken out of service once the aging knee happens, or shortly after the aging knee happens, as I explained in the next slide. The aging test for the lithium iron phosphate battery shows also a very consistent and linear degradation for the batteries in their second life. These batteries can last up to 6,000 cycles because they don't exhibit any aging knee, and their internal impedance also shows a very consistent, but not very much of increase in their second life. So these batteries are very good for second life. I mentioned about the aging knee detection. In our laboratory, we developed a method which is very simple, a simple linear method to go with the aging process. Once the battery degradation cross the linear curve that we developed, we think the battery is reached the aging knee and they have to be taken out of service soon after that. We have applied this method for different batteries inside the laboratory, and we have very consistent result. Next step is that move on to what it is this second life EV batteries for solar PV storage. First of all, we designed the architecture based on the pack level, because disassembling these battery packs to get the cell is very time consuming and which may physically impossible or economically infeasible to do it. So we designed this battery storage system with a battery pack connected to a DC-DC converter. For the diagram on the left hand, you can see we have 8 batteries connect to 8 DC-DC converters. The output is connected in the DC junction box. They go to the inverter. On the right hand, we have 4 batteries. Each are connected to DC-DC converters in order to increase the power of the output. But they're also connected. The DC-DC output is connected to an inverter, which is connected to the building. In order to use this battery effectively in an energy storage system, we have to develop a BMS gateway. The reason is that each battery pack comes with a BMS. We can read the data on the BMS. However, this BMS sends out a CAN message which contains the battery information with the identical ID from each battery pack. Therefore, we cannot simply connect them in a CAN bus. We designed this BMS to read the BMS information and then stamp them with a different ID, and then send this information to an energy management system so that we can know which information belongs to which battery pack. This battery BMS gateway have already been tested in the laboratory and it will be deployed in the site very soon. In order to use this battery effectively, we have to put them in a container because we don't want to put these batteries inside the building. Just in case something happens, it might blow up the building. In order to put them in a container, we have to be very careful about the space usage. So in this case, we designed a rack inside the container so that we can hold multiple batteries inside the container. In the meantime, we have to insulate these battery containers so that we can maintain a certain temperature in hot and cold days. We did a thermal simulation so that we can put enough cooling. In this case, we found that a window type air conditioner at roughly 22,000 BTU will be sufficient. And this air conditioners cost very much, not very much, like less than $1,000. We also designed a structure inside the container to hold all these batteries. In the example, we hold 2 batteries in a row, but in the real application, we have to hold up to 3 to 4 batteries, and each battery can be as much as 1,100 pounds. So 4 batteries stacked together, including the frame, will be roughly 5,000 pounds. The structure has to be strong enough to hold the battery to the floor and also to the side. In case there's earthquake, this battery will not flip over. We also put the inverter, DC-DC converter, the UPS for the management system, and other auxiliaries inside the container. We also developed a phone app so that we can display the information remotely on the phone, such as the battery state, the charging power, the discharge power, the SOH, the sound generation, and so on. We also developed a model predictive control for the battery system so that we can save maximum amount of cost for the building. Through this MPC, they look at the historic usage, the historic generation of the PV system, as well as the weather condition, so that we can plan ahead of time to charge the battery, for example, from the battery the day before if we have a lot of solar generation, or we deliver power to the building when there's not enough solar generation. We deliver power to the building during peak usage or peak rates to reduce the cost of the building. We have to understand how much battery we need for each building. So we developed a size optimization algorithm so that we can design the size of energy storage system for any building based on its historical usage and the PV generation. We are going to deploy 2 pilot testing sites, and they are under construction. So one site on the left hand shows that we can save $300,000 minimum for 10 years of the battery life. The cost is $96,000. Now we have to remember this is only a pilot testing. The cost is much higher than if this is a commercial system. The system on the left side will cost $86,000, but it won't save that much of money because the building is small and the usage is low. However, the building is a bio-size lab. If the battery goes out of power, like during a power outage, it's going to cost owner anywhere from $50,000 to $100,000. So the energy storage system deployed, even though it doesn't save that much money, it helps owner to save money during a power outage. The system is designed to sustain power for minimum 24 to 48 hours during a power outage. The system is designed in a 20-foot container, which includes 6 battery packs, a DC-DC converter, and an inverter, energy management system, and all the circuit breakers, a UPS, power supply for the lighting, and the energy management controller, as well as some needs, emergency needs, and the container is connected to the solar and the building power electrical room, and then they can go to islanding process during a power outage. So that is what we have done with the second life UV battery for energy storage system in commercial buildings paired with a PV system. In addition to the second life UV battery, my group also conduct other research activities, including the wireless charging system that we have worked with a lot of companies, DOE, and we have developed some technology to increase efficiency and also this foreign object detection for wireless charging systems for EVs. We also conducting research in battery diagnostics and prognostics. In particularly, we are interested in knowing when the battery will have a failure, and we can mitigate those failure ahead of the catastrophic event happens. And we also developed offline cloud-based battery state of health and the prime estimation using this BMS data from vehicles. And this can provide the battery manufacturer with the state-of-the-art technology to learn or to know what happens in their vehicles. And it can even update the battery parameter during the operation of the battery, like periodically, like every couple of months when the battery is in service. Another project we are conducting right now is working with NASA to develop a vertical takeoff, vertical landing electric airplane. The reason for this electric airplane is that these electric airplanes are very quiet. They can carry 4 to 5 people, 600 pounds of goods, and they can fly very fast. In currently situation, our rescue medical transport, like transporting transplant, organ, emergency rescue, things like that, we use helicopters because they can take off from the roof of a medical building. But the problem that they're very noisy, they don't travel very fast. Sometimes they don't even catch the time for organ transplant. So with this electrical airplane, they can take off vertically and land vertically, so they don't need a large platform. They can travel very fast, up to 300, 400 miles per hour, so they can be used for all these future applications very effective. Our group conduct all this research, and also we have created a wireless power YouTube channel. So if you are interested, you can click on this link to learn the latest technology and also the fundamental principle of different technologies associated with wireless charging, second life UV battery, electrical vertical takeoff and vertical landing airplanes, and so on. Also the textbooks related to these areas. With that, I'm going to conclude my talk, and I'll be happy to answer any questions you might have. Thank you very much.